It's my pleasure to now introduce Sabrina Strauss now we're going to switch to University of Notre Dame. So in the physics department, again, Lawrence Livermore National Laboratory, 2014. And her talk, which is actually the same title, which is always nice to see, is Beta-Delayed Neutron Emission using the Beta Paul trap. So Sabrina?
So can everybody hear me? Okay. So I'll be going through basically 3 different parts. I'll be explaining what beta-delayed neutron emission is, what the beta Paul trap is, and then basically the results of our experiment. And I'll also be explaining why we actually care about the beta-delayed neutron emission, I promise. But the first thing is, the first part of beta-delayed neutron emission is actually the beta decay. And in our beta decay, we care about beta minus decay, which is when in our nucleus, one of the neutrons turns into a proton. It releases some energy, Q beta, that can be released through kinetic energy through either the beta particle, the neutrino, or the daughter of the nucleus. You can also have excitation energy in the daughter of the nucleus, which releases gamma decays. We're going to care about those later, I promise. Beta-delayed neutron emission is a special kind of beta decay, where we actually have so much energy released in our decay that we're above the neutron separation energy. For those unfamiliar with that term, the neutron separation energy is essentially if you were to take this daughter nucleus, xenon 137, and then split it up into a free neutron and xenon 136, the difference in the mass between those equates to an energy that's known as the neutron separation energy. So what happens is our nucleus decays. We can actually decay to an energy in our daughter nucleus above the neutron separation energy. When that happens, we actually can emit a neutron instead of emitting our gammas. That is beta-delayed neutron emission. You can only emit the neutron after you've emitted the beta. So there's 2 different things we can actually get from beta-delayed neutron emission. The first is our neutron emission probability. So what's the chance that we're actually going to emit the neutron when it decays? And then the neutron energy spectrum. This winds up being really important because you actually, depending on the energy of the neutron, as Marina talked about earlier, she needs thermal neutrons for these reactions to happen. Well, different energies of the neutrons have different cross sections, so knowing the actual energy spectrum of the neutron is pretty important. So this is actually why we're interested in it, is how are the elements made? I have 2 pictures here that are both astrophysical processes. This one is actually the Crab Nebula. It's a supernova remnant. And then over here, we have an artist's rendition of a neutron star merger. The reason I chose both of these is because they're 2 possible sites for the R process, which is the process that we're interested in, and the one that really gets affected by beta-delayed neutron emission. But that's not the only process. What I have here is actually the chart of the nuclides. For those unfamiliar with the chart of the nuclides, if you were to take the periodic table of elements and put it and just stretch it out into a line along the y-axis, and then put neutron number along the z-axis, you would get this picture. Basically, instead of each element having its own box, each isotope of each element has its own box. There's a black area right here. Those are actually, it's known as the valley of stability. Those are very stable nuclei, the ones that you and I encounter every day and everything is made out of pretty much. These different lines are different astrophysical processes. Fusion, right here, goes up to about iron. That's the one that our sun is doing. It's currently at a much lower stage. It's not necessarily going all the way up to iron, but that's basically our main stars are doing this. Then we have the S process, which is our yellow line here. S, it's slow neutron capture. Basically, there's enough neutrons around that the nuclei close to stability are capturing them, then decaying back to stability and repeating the process, slowly climbing up the chart. The RP process is known as rapid proton capture. And what this is actually in what we consider the proton-rich area of the chart. It's above the valley of stability. And it's actually, as the name might imply, rapidly capturing protons. It gets limited around mass 100 because of alpha decay. The one we care about is our R process, which, as you might notice, actually goes out into areas where there's nothing coming from the chart. The reason for that is actually because we go into such a neutron-rich environment that we haven't been able to observe it yet. This blue line is actually what we predict is going to be the number of observable nuclei. But we haven't seen it yet. So actually studying the R process is very difficult because there's a lot of areas where we have no information. In and of itself, it's a very simple idea, just involves thousands and thousands of nuclei. You have some starting point, and then you rapidly capture neutrons. You also have a competing process where you have photodisintegration. Eventually, you reach a waiting point. At this waiting point, finally, it'll beta decay. Sometimes it will emit the neutron also. However, this doesn't always happen, and when it actually matters is going to be near the end of the full R process, which in and of itself, we believe is a very short process. The rapid is there for a reason. So in the R process, we actually have a lot of nuclear physics that goes into it. Our neutron separation energy, we already talked about, that affects the direct path that the R process takes. Our time scale is actually affected by the half-lives of the nuclei. Our beta-delayed neutron emission branching ratios affect the final abundance pattern because we hit a point that's called freeze-out when you no longer have the neutrons to continue the R process. So at freeze-out, we actually, these are one of the main sources of neutrons at that point. It also will affect the final mass values. Fission winds up becoming very important because it's actually an endpoint. We eventually hit a point where we can no longer continue capturing neutrons, or you get something like uranium, which has neutron-induced fission, which then just adds more nuclei back into the system to continue going up on the scale. And then finally, we have our neutron capture rates, which you might remember I said that depends on the neutron energy, so we also need the energy spectrum of our neutrons that are being emitted. And this also affects our final abundance pattern. There is, of course, this isn't the only reason we care about beta-delayed neutron emission. We also care about them in nuclear reactors because the fission products from these from neutron-induced fission of uranium actually can also emit neutrons, so that adds to the neutron flux. Now, the question, of course, is how do we measure beta-delayed neutron emission? The simple answer is, well, you measure the betas to figure out that it's beta decaying, but then you have to measure the neutrons. Unfortunately, measuring neutrons is not easy because they are neutral. There is a reason that Marina was not focused on measuring the neutrons and was instead focused on measuring the gammas. Unfortunately, we can't do that quite as easily. So in general, this is sort of one of your standard cartoon versions of how you would measure neutrons. You would actually moderate the neutrons down to a thermal energy so they can easily react. And then we have a reaction product that's much easier to detect using our standard charged particle detectors. This is not the only way you can detect neutrons, but it's one of the more standard ways. The problem is that when you do this, the way you actually measure the energy of the neutrons and things like that is through time of flight, which means you have to have the detectors far away to have a well-defined distance to get well-defined time, which means it gets very expensive to be able to cover a large area and to get a good solid angle. So we asked, what if we could cut out that reactive layer? What if we didn't have to detect the neutron directly? Well, the initial decay already has a charged particle in it, in our recoiling ion, our daughter particle. The thing is, normally you can't detect that very easily because we usually implant it in a detector or in a tape station in some kind of lattice, and it doesn't actually have enough energy from its recoil to get out. So we had to ask ourselves, is there a way that we can trap it in a place without it being trapped in a lattice so it could freely move around? Because it only has something on the order of EeV or maybe KeV of energy. And that's just because of basically the conservation of momentum from when the neutron comes out. Or in this case, the electron, which is even lower because the electron is about 1,000 times less massive than the neutron. Well, that's where the beta-Paul trap comes in. Now, when we used the beta-Paul trap, we did the experiment at Argonne National Lab using CARIBU at ATLAS. ATLAS is the Argonne Tandem Linear Accelerator System. The tandem is no longer there, so I actually like to refer to it as ALAS. But we're actually going to focus on CARIBU. CARIBU is the Californium Rare Isotope Beam Upgrade. It's a Californium-252 source that sits right here. It's about 350 millicurie, and it has a spontaneous fission of about 3%. What happens is it spontaneously fissions into our gas catcher. Now, what a gas catcher is, it is filled with gas. It has an RF carpet, radio frequency carpet, that basically causes it an electric field and collimates the beam for us. We collimate the beam and send it into an isobar separator. For those unfamiliar with the term isobar, it just means same mass. We basically select our mass out using the isobar separator. This isn't a perfect system, so we do get some contaminants, because even if we're looking at, say, iodine-137, we'll get a little bit of tellurium-137, which is slightly heavier than it, and a little bit of xenon-137, which is slightly lighter than it. From there, we deflect it and send it down to the low energy area, which is why we don't go into the main part of ATLAS, because we actually want to stop these ions so we can't have them going very fast. We bunch the beam and send it here, which is where our beta Paul trap is. Now, the beta Paul trap is, uses electric fields only. There is another kind of ion trap that I will not be discussing today that is used for mass measurements. But the Paul trap is basically 4 electrodes that have 3 segments. So the ions will come in this way. When they get in here, we'll bring the voltage up on the 2 outside ones. What happens is then it repels the ions, and they can no longer escape in that direction. So we've isolated it in the beam direction. To isolate it in the x and y directions, we actually use another radio frequency electric field. So this electrode and this electrode will both be at the same voltage, and then these 2 electrodes will be at the opposite voltage. And we will actually alternate the voltages on them. So the beam will the electric field will keep changing from going in this direction to this direction, which means that the ions can never accelerate, and they actually effectively get caught inside our trap. Hence its name, being a trap. So now we've caught them. This was the actual configuration for our beta Paul trap. Between each electrode, we put our different detectors. Here we have the detectors for the beta particles. The MCPs are multi-channel plate detectors. We use those to detect our recoiling ions because they're very sensitive and very efficient. And then we have germanium detectors for detecting the gamma rays behind that. What we have here is actually a picture of what we would see, where we use the start of seeing the beta detector and then looked for our recoiling ions. Because the neutron is so much more massive, it has a much faster time of flight, and we're actually able to very easily separate out the beta-delayed neutrons from the regular beta-decay daughters. There's 3 ways we can actually measure the beta-delayed neutron emission probability with the BPT. I will be talking about each of them. I promise this is the only equation that actually has slides on it, though. And so each of these was basically focused on by a different graduate student. I specifically was working on the beta gamma, and each of these has their own limitations. So it's a really nice way because they have all these systematics that you can check to make sure that the systematics are not affecting your overall answer, because they should all agree with each other. In this case, in the beta singles case, we'll be talking about a model. In the beta gamma case, the biggest issue here is actually that you have to know the spectroscopy beforehand, or we have to come up with a way to figure out the spectroscopy from the data we have. And then in the third method, you have to deal with the fact that it is not a perfect system, and you do have some ions that are not coming directly from the nucleus of interest. In the first method, the beta singles method, we have to take into account what it looks like over time for the betas that we're getting. So we actually had a full cycle time. And what would happen is, because it's not a perfect system, sometimes particles would get stuck on the sides and give us extra signals. So we actually had a period where we wouldn't have anything in the center of the trap to figure out what our background time was. In this case, which was for cesium-144, we actually had a background time of 3 seconds. Then we would start injecting our bunched ions into the trap every 0.6 seconds. And we would do this up to a total time of 9 seconds. What happens here is these decays and this decay pattern actually winds up being representative of of the population of the trap. And we're able to model that. So this is a little bit busy, I know. Basically, we have 6 different populations we need to take into account. You have, in this case, cesium-144, xenon-144, which is its parent, and barium-144, which is its daughter. And then each of them has both a trapped and an untrapped component. So this black line is our fit to the data. This blue line is the trapped cesium-144. This dotted blue line is the untrapped cesium-144. And then here, you can't see it very well, but there's actually trapped xenon right down here. There was no trapped barium, and then this is the untrapped barium that comes basically from the decays. So we're able to model all of this. The problem is we have to make a lot of assumptions about efficiencies and things like that, that even though we do our best to measure them, it's still not necessarily going to be 100% right all of the time. So having the other two methods is really helpful. In the second case, we have our beta-gamma method. Now, I specifically chose a really nice slide because and it's even funnier because Marina was talking about the potassium-40 before. It's called the beta-gamma method because we aren't just looking at our gamma rays, we're also looking at them in coincidence with our beta detector. And in that case, what happens is this is the singles, as soon as you gate on those betas, this potassium-40 line disappears, all of those lines disappear. This is extremely important because the reason that you're seeing all of those, concrete is a great moderator for radiation and for blocking radiation. It's fairly cheap, but it has a lot of gamma lines in it because it has those natural uranium and thorium decay chains as well as the potassium-40. So once we gate on it, all of this is just, all of these lines that are there are all from iodine-137 and tellurium-137 and xenon-137. We also were able to eliminate the trap background. I showed you before in the cycle that there was some basic trap background. Well, it winds up artificially inflating the number of decays that we actually have because of the background, and we can't rely on any of that background information because all of our efficiency is calculated assuming that we have our ions coming from the center. So right here you can really see that there's actually these are all iodine-137 lines, and you can really see that they're getting populated in the background data. So we can subtract that off and then be able to calculate our efficiency. Now, or not our efficiency, our number of decays, which is based partially on knowing the spectroscopy of what is the branching ratio of that line, which is why the spectroscopy is so important. We can't just assume that all lines are created equal. Now, we didn't actually get to do this because antimony-135 was the only case where this was really beautifully shown and you could tell it was there. And unfortunately, if you can't tell from this, it's pretty low statistics. But we actually, in some cases, can see the gamma daughters of the gammas of the beta-delayed neutron daughters. In that case, you might be able to directly calculate what PN should be or more information about that. Now, the two lines I've marked in red are both from antimony-135. It's a beta-delayed neutron daughter. We were able to actually just use this to check for consistency. And if we assumed the literature value for the neutron branching ratio, it actually did agree fully with the other antimony-135 values, which is a really good sign that we're not totally crazy and something is working. And then our final method, which is our recoil ions, is actually a really nice check, fairly quick check of making sure things are working. As I said, this is actually also gated. In this case, we started with a time of flight. This is in nanoseconds. Or is it milliseconds? Oh, no, it is in nanoseconds. I forgot that it was written there. We started with a time of flight. We start by gating on a signal from our beta detector, and then we look for our recoil ion. Now, the problem with this is that because it's not a perfect system, you have to deal with isobar subtraction, which is a little bit more difficult in this case than in either of the other two, but it's still usable. What's more is because this is a time of flight spectrum, and as I told you before, you can get the neutron energy from time of flight. Well, the energy of these recoiling ions from the beta-delayed neutron emission is directly proportional to the energy of the neutron it emitted. So we can actually use this time of flight the same way we would use the neutron's time of flight and actually get our energy spectrum as well. We can also see the difference just looking by eye at different nuclei to see that we're getting these different isotopes and to see that there actually are different values. So in the case of cesium-145, it has a neutron branching ratio of a literature value of 14.5, and that's about twice the iodine-137. You can really see the difference in the fast ions versus the slow ions in the two cases to really be able to tell that they actually are different PN values. So that's a really nice quick check as well to make sure that our data is working. And then you can also tell that these are actually different shapes, which is good because you should have different shapes for your neutron energy spectrum as well. Now, these are results from 4 of the 8 isotopes that we actually ran. And I had to stamp preliminary on all of these because we're still playing with the isobar subtraction. We're still playing with the last of our systematics. And what you can see, it may not look immediately to you like things agree. This is actually only a 1 sigma bar. They all agree within 2 sigma, which is a very good sign. That's the standard we're currently using. We'd love for them to actually be even closer. But they all also agree with previously evaluated values for this data, some of which I actually don't agree with the error bars on because this is only from 3 measurements, and they all wildly disagree. We do have plans for the future. We actually are finalizing the analysis, and we're looking at doing 2 to 3 papers based off these 8 isotopes. And then we have the next generation trap that we want to build, which should have more detectors. It should be more efficient, get rid of some of the systematics. For instance, we actually do have a systematic we have to take into account from the electric RF field that I talked about earlier. And we already have approved to measure 3 isotopes of tin in the next generation trap. And then this is a list of the collaborators along with all of the different support grants that I knew we had, to say the least. And those highlighted in red are basically the people who have been the main people doing the analysis. Thank you for your time.